Happy May the 4th, everyone. We're going to go ahead and get started. Just as a reminder, please make sure you turn off all sounds from your electronic devices. We have up Pablo Galindo, who is a Python or CPython core developer and also works at Bloomberg. He'll be giving time to take out the rubbish, garbage collector.
Awesome. So thank you everyone for coming. So in this talk, I'm going to walk you through basically the current implementation of the CPython garbage collector. So at the beginning, we're going to make a gentle introduction of memory management and reference counting. But the idea is that we are centering our efforts on how the current algorithm for garbage collection works and why it's needed. So a very brief introduction. So this is my Twitter handle. I am a Python core developer. I work now as a software engineer at Bloomberg. Before that, I was in academia doing black hole physics research. So if you're interested in that, please come after the talk and talk with me. I'm one of the authors of PEP 570, the implementer. We merged this last week. Well, yeah. And I spend my free time squashing bugs and race conditions on CPython. Awesome. So let's get with an introduction of what garbage collection is and why it's needed. So imagine that you have a variable, right? And for example, here is this list, and then you delete the variable. As you know, this is basically removing the name, but we're interested in what happened at that point. So this scenario also presents itself when you have a function, for example, in this case, this factorized function, and then you have an internal variable local to the function. In this case, is this list of primes. And when the function finishes, the list of primes is not needed anymore. So we say that the variable goes out of scope. And we're interested to know what happens or how CPython behaves to clean up that list that is not needed anymore. So what happens to it, right? So some definitions. So first, we are going to define garbage as the memory that is occupied by objects that are no longer needed in the program. And therefore, garbage collection is just a form of automatic memory management. We can go to the actual Python glossary and we say how it defines the process of freeing memory when it's not used anymore. So why we need this thing? Because otherwise, we will run out of memory, right? If we don't clean the memory that we are using, we will soon run out of memory. And the idea is that it has to be automatic. And this is very important because first, we don't need to do it ourselves. This involves less thinking and therefore fewer bugs because all of you that have compiled languages, and especially low-level ones like C, you may know that memory management is one of the most challenging parts of the language and the source of many of bugs and memory leaks. There is a problem, though, because having it automatic can be a bit slower if it's not done properly. So nowadays, modern languages tend to not do it manually. So for example, Rust. Rust is a good example. Rust doesn't have garbage collector. It has a very clever new approach, which is the borrow checker. So this is a way, apart from giving other nice features, it's a way of avoiding sort of manual memory management or even garbage collector. So C and C++ usually were designed for having manual memory management, but there is some implementation of garbage collected version of the language available. Okay, so let's walk also through some pieces that we're going to need to understand the algorithm and the different phases that it went through. So the first thing that we need to talk is finalizers. So basically, imagine that we have a class, in this case, this class dog, right? And then we create one of these dogs, and then we delete the dog. And then we assume that this frees our memory, right? So it's actually a bit more complicated, because if we go to the Python docs, we will see that it's actually not guaranteed that the del method is called, especially when the interpreter exits. Usually it's actually called, but we cannot rely on that method to be called. Why not? Well, because the first thing is that the purpose of the del method, which is called the finalizer, is only to free up memory when it's no longer necessary. So we should not rely on this method to do some kind of cleanup of resources. We have other approaches in Python, particularly with the statement and context managers, that will help us with these things. So for example, if you are going to close a file or finish a database connection, you should use a context manager and not del. Then we are going to introduce reference counting. So reference counting is one of the, basically the major way that CPython manages memory and lifetime. So reference counting is a strategy. So the idea is that every object has internally has a number which basically refers to all the other objects that are referring to it. For example, you have a list and an object is inside the list, then we have the number will be 1 because the list owns the object. For example, in this case here, we have x, which is a list of 3 elements, and then we create a second variable. So we say that x has 2 references. One is the name x, and the other is the name y. You can actually try it for live objects. So for example, in the sys module, we have this function called getRefCount, and you can call it to any object, and it will return the number of references that are pointing to the object. So basically, internal integer that lives inside the object. There is a catch, though, because the function will always return 1 more. And this is because the function needs to see the object to return the reference count. So you need to be aware that you always need to think 1 less. So for example, let's make an example. So we import the module sys, and we have this list that we talked before, and then we check how many references it has. It says 2. We know that actually it's only 1. Then we click another name for the list, which is y, and then we check again, and we see that actually it increased 1. We know that actually it's 2. And then when we delete the name, we say that we're back to 2 again. So that's OK. You have to be aware as well that a container also claims ownership of this. So if it's not only names to the variables. If the variable is inside a container, the reference count will also be increased once. For example, in this case, we have 2 variables. So if we check the reference count of x, we know it's 1. But when we put this variable in a set, we see that actually, because the variable is in a set, the reference count increases by 1. And the idea is that when the reference count goes to 0, we know that no other object is actually using the one that we are talking about, so we can actually destroy the object, right? So now we're going with the problem, which is cycles. So let's imagine this situation. I'm only using 2 nodes because 3 is like a tree, and people just shut down attention when there is a tree in the slides. So in this case, we have A and B, and these objects point to each other. And then there is this arrow on the left, which is basically a reference from the outside. So some other object outside is referring to A. So A has 2 references, 1 from B and 1 from the outside, and B has 1 from A. So there is a problem, right? Because if we delete the reference from the outside, then A points to B, but B points to A. So even if these 2 objects are not reachable anymore, the reference count will never fall to 0, and therefore we cannot clean them up. So we need something else, and this something else is the garbage collector. So the situation, for give a bit more clarity, will be something like this, right? We have a lot of objects in our program, which are here the blue cycles, and then the blue circles. And then we have these 2, A and B, sitting around, and they are not reachable. This means that there is not an arrow from these other objects pointing to them. So we need something else, some mechanism to identify these cycles and delete them. So this is a garbage collector. So to walk through the algorithm, we are going to imagine basically a situation in which we have several cycles. So first, we need to know how these cycles are created. So for example, this is a simple example. You can create a class node. You can create 3 of them. And then setting attributes, you can basically make every node point to the other 2. The situation is actually more complex. This is an actual diagram of the relationship between all these classes. You don't need to actually understand this thing, but bear in mind that there is actually much more hidden objects that have reference inside. In particular, you can look how there is a lot of things that point to the node type in there, and that is actually one of the major sources of cycles that you can form. So the situation, even if you think that cycles are a bit weird, it's actually very, very common that happens. So it's important to have it handled in the runtime. So OK, so let's go through the algorithm. So bear in mind, the idea is to identify cycles and remove them. So first thing, how we're going to identify the cycles. So OK, as an example, let's consider the following situation, which is this one. So let's consider these three cycles, which are separated. We have X, Y, and Z, which is like a triangle of cycles. Then we have A and B and L. The form is not important. It's just to have 3 of them that will yield different behavior along the algorithm. So basically, the triangle is created as we saw before with our class node and internal reference. And notice that we have an extra cycle that will help us see some behavior later with this set that points to itself. Then we have A and B, again, with our class node, and both A and B point to itself. And an interesting one, which is a list that contains itself. This is a cycle of only 1 element, which is cute. Cool. So bear in mind also that the situation is a bit more complex because every object has a dictionary inside, and is the dictionary the one that actually points to other things? So we have to consider not only the ones that we saw before, but every dictionary associated with the class. So this is the situation, right? We have all these arrows pointing to each other. So in the first row, we have the objects. In the second row, we have the dictionaries and the list that has no dictionary inside. And then the algorithm uses two linked lists. The first one is the linked list of all the objects that are being considered. And the second one is a list of all the objects that are going to maybe be destroyed. And I say maybe, and you will see why. So the first step is identifying which are the cycles. So for that, we basically are going to copy the reference count into a separate field because we are going to modify, and we don't want to mess in case the objects are not going to be destroyed. So in this case, the algorithm starts basically copying this thing and decrementing the reference count of all the objects that are pointing for every one of them. And then when an object has a 0 reference count, we might mark it as maybe unreachable. So for example, these are the numbers that are for the reference count. So we start with the first object, and we decrease the reference count of the only object that is pointed by x, which is the dictionary. So the dictionary becomes maybe unreachable. That is what is marked in a gray color. Because it has a reference count of 0. So we go with y. Y points to the dictionary. We decrease its reference count. Same thing with z. The dictionary of x actually points to y and z. So y and z are decreased by 1. The same thing for y. And when we reach the dictionary of z, then y and z are no longer referenced by anything. So both become maybe unreachable again. The same thing happens with a, b, and its dictionaries, right? And then the list that points to itself only has one reference, we decrease it. So if you see in this situation, what happens is that after this algorithm, only the objects that are reachable from the outside, which is that arrow that you see up there, has a reference count bigger than 1. So basically, these are the objects that are reachable from the outside. And all of the rest are basically isolated cycles. OK. So now we are not finished, because as you may imagine, if x is reachable from the outside, we cannot delete any of the things that are actually referred by x, right? Because we will destroy the internal state. So the next part of the algorithm is trying to figure it out which objects are actually reachable for it. So the way it works is that we start with the first object. If the object has a reference count bigger than 1, we mark it as certainly reachable, which is going to be this green color. Notice that we also mark x, because x is the only object that is reachable, sorry, the dictionary of x, because the dictionary of x is the only object which is reachable from x. OK, so we know that these two are reachable. Then we go to y, and y has a reference count of 0, so we don't know if it's going to be reachable or not, so we will move it temporarily to the list, the second list, which is the object that we maybe are going to destroy. The same thing happens with z. Then we visit the X dictionary, and the X dictionary is very interesting because it's pointing to Y and Z. And notice that Y and Z are already in the second list, which is, oh, maybe we are going to destroy them. But because they are being pointed by an object which is green, we know that those, we cannot destroy those. So we need to move them back to the first list. And we move them green because we know that certainly those are reachable. Then we go to the dictionary of Y, and it has 0 reference count, so we move it to the second list. The same thing happens with the dictionary of Z, A as well, B as well, and the dictionary of A and the dictionary of B. So we are basically moving all of these objects to the second list because they have 0 reference count. Notice an interesting thing, which is that every time we have one of these red arrows, all the objects to the left are green. This is an invariant of the algorithm, and it's very important when you're implementing it, because if this is not true, you have a bug. And then with L has 0 reference count, we move it as well to the second list. And then we need to visit Y. Notice that Y is visited twice. Like the first time we visited, it has 0 reference count, so we move it to the second list. But the second time we visited, it was moved to the first list because someone else pointed to it. And we need to repeat the algorithm, like which are the objects pointed by Y. So actually, it's the dictionary of Y. So we move it back from the second list to the first. And then the same thing with Z. The object pointed by Z is the dictionary of Z. Also X and the rest, but we know that they are reachable, so we don't need to do it. And then we visit the dictionary of Y, but everything that is reachable from here, we know is alive, and the same thing for the dictionary of Z. So when we finish this step, basically we know that all the objects that are reachable from the outside, so they are marked as green, and the objects that are marked as gray, we know that they're isolated. So this is objects that form cycles, and they are not reachable from the outside. And I'm repeating this because it's very important in some of the assumptions, one of the things that we're going to do afterwards. And it's very important to bear in mind that nobody outside these objects that we have here can refer or see any of these objects. So right now that we know the objects that we need to destroy, we simply destroy them, right? So it's actually no, because nothing in Python is actually that easy. So there is this thing called weak reference. So what are weak reference? So weak reference are basically a way to referring to objects that don't count towards the total sum of reference counting. This is especially useful for not forming cycles in the first place. But it has other usage, especially, for example, if you are wrapping C++ or other languages that have problems with deterministic destruction. And weak reference are especially tricky because weak reference have sometimes callbacks. So basically, the idea is that if you have many weak reference to a certain object and the object dies, all the callbacks are executed. Basically, it's a way of saying, oh, the object that I'm referring to have died, so I need to do something else, right? Like maybe closing files or maybe removing other cycles. So these are very tricky because every time you call a function when you're finalizing objects in CPython, you have to be extremely careful. So in our case, we know that these are the objects that survive the last pass. So these are the two blue objects that we know from before and the list that contains itself. So we have two kind of weak reference that we saw before. So here, the ones that has the little f of x are the ones that have callbacks, and the other two, so it's the green ones, right? And the other two are weak references that do not have callbacks. Okay, so for the one that do not have callback, we can just remove them. So the weak reference are stored actually in a linked list, which is hidden from Python that lives inside the object. So we just reach into the linked list and we unlink them and destroy them. So for the ones that have callbacks, we have to be very careful because it can be two possible situations. One is that their weak reference objects are actually outside the cycles. Remember that this weak reference cannot refer to the objects inside the cycle, so that's okay because they cannot mess with them. But we have to be extremely careful with the second case. The second case is one of the objects that we're going to destroy as part of the cycle happens to be a weak reference to one of the others. And this is especially complicated because the callback of the second one can actually mess with our object. So for the first one I said, we can just remove them because there is absolutely no risk. They cannot reach the object in our cycle. They cannot create new references or resurrect them or change the field. So we just remove them. For these ones, so the danger, as I saw, is like resurrection, which is like the callback can actually increase the reference count again, and we can bring it back to life, so more later on this. But there is a trick, which is that the garbage collector doesn't guarantee order of destruction. And under that assumption, we can pretend that the reference count, the weak reference, sorry, just happens to be before the object, and we just don't call it, because we say, oh, the weak reference was actually destroyed before the object was destroyed, so there's no reason to call it. It's a trick, but we can do it because we have these guarantees that I talked before. Okay, so we have called all the weak reference, so we can forget about those. Now let's call out finalizers, which is the second problem. So finalizers are especially tricky as well. Why? Because let's imagine this situation. So we have A and then we have B, and they point to each other. So the finalizer remembers that are the del method that you can implement in Python. Inside is a function pointer called tpfinalize. In Python 2.7 or well, at some point it was a legacy one called tpdel that was linked to also to the del function. But as we will see later, that's legacy and has been replaced with a better system. So the problem is the following, like we have these two objects and we need to destroy them, and then we need to call the finalizers. But we have a problem because which finalizer we need to call first, right? Imagine, for example, that the finalizer of A needs something in the finalizer of B. Imagine, for example, that A is a database and B is a connection or something, and when you are going to destroy the database, you want to make sure that the connection is closed or something like that, right? Which is not the best way of doing it, as we saw before, but imagine that is a possibility. Also, what happens if the finalization of A calls the finalization of B for whatever reason? So we don't know the order. And there is another problem, which is, for example, this one, which is resurrection. Imagine, for example, we have a global variable called x, we initialize it to none, and then we have this class that we implement the del method. We print something to know that it was called. And then basically when the del method is called, we put the object in the global variable. So basically this is resurrecting. The object is going to be destroyed, but it just happens that the del method points the object in the global variable, increasing the reference count and putting it back to life. So in this case, when you create one of these objects and destroy the only name that points to it, basically the print function is called, and we see that the x variable instead of none now is our object. So this is especially tricky because this can mess up with so many things. It's actually so tricky that Python 2 decided, if there is one of these and it becomes in a cycle, I'm literally not going to do anything. And indeed, we can actually check that this is true. So this is Python 2, or more known as legacy Python. So we have this class node. We implement this del method. We print something to know that it was called. It's the better debugging strategy. And then we create one of these two nodes. We create a cycles pointing A to B and B to A. And then we destroy both names and force a collection. In this case, we are forcing a collection there, basically calling gc.collect, which is a function which is available in the gc module. So basically, this runs the algorithm that we saw before. So after that, we saw that these two objects are actually not destroyed. They are in this special list called gc garbage. So there, and basically this means that they are never destroyed. They're going to be there for the remaining of your program, and this is more or less a leak. So in Python 3, we have perf442 by Antoine Pitrou. And this fixes this and adds safe and deterministic object finalization. So this takes into account all the things that are very, very complicated, like resurrection. It takes into account also something very important, that is that the destructor here is finalizer, but every finalizer is only called once. So basically, if the object is resurrected and then destroyed again, the del method is not called again. And also, it takes into account safety and correctness. So if we repeat the same experiment again, so we create the node, we create two of them, we create a cycle, we force a collection. We know now, with our incredible debugging strategy, that we see that both prints have been called, therefore the del has been made. And you can actually check that A and B are no more. So how this works? So inside the object, there is this function pointer called tpFinalize. The tpFinalize is basically pointing to your del function. So these are the objects that we have before from the algorithm. And the idea is the following. So for every object, let's start for the one which is the first there. So we call the finalizer if it's present. If it's not present, we don't care. If it's present, we'll call it. Here, we're going to represent that with this green circle. So that means that it's called. Then, inside the object, we mark that we have called the finalizer. So we are going to represent that with this tick. This is very important because this means that every object needs to know if the finalizer has been called. And this is something that we need to store inside the object. And this is true for every object which is tracked by the garbage collector, which means that absolutely all the objects need to have an extra field inside somehow, therefore increasing the memory consumption of all your Python program. Imagine that all your Python objects will have an extra little field, but when you add them all together, it can be an important increase. So when you do this kind of thing and when you modify the Python object struct, you have to be extra careful not to add like arbitrary stuff, because if you do this thing, basically you're going to increase the memory consumption of all the programs that use Python. So then, you have to also be very careful, because another thing that can happen is that when you call the finalizer of the first object, it can actually go and destroy some of them. So for example, the finalizer of the first object can go and destroy the last one. And this can happen. So in this part of the algorithm, you have to be extremely tricky, because when you have the collection of the objects that you are iterating over, they can start appearing and disappearing. And then your algorithm needs to be resilient of this effect. This is one of the parts of the garbage collector code which is full of comments explaining how crazy this is and how careful this needs to be. But it works, sort of. It works. So then we know that this can happen, and then the second time we call the other object finalizer, and we mark it as finalized. And this little mark is the one that we need to inspect the next time we try to call the finalizer, because if the mark is there, we know that the method was called before, so we don't need to destroy it. So you may think, okay, this is okay, but what happens if the first object is actually resurrected as we saw before? So if the object is resurrected, it means that we need to abort all the collection. It means that that object cannot be actually destroyed because it has been resurrected, but not only that, all the other objects that have been referred by that one need to be also resurrected as well, because you cannot leave the object in an inconsistent state. So basically, you abort the collection and put all the objects back. But that's basically all the possibilities that can happen. You just need to be very careful with where you put things, and that your data structures are very consistent. So if you check the code, there is actually a lot of assertions around this, and the algorithm checks all the time that all the collection that it's using is consistent, and the reference counts are bigger than 0 at this stage, and that the different objects that happens to be there are never deleted. So the last step in the algorithm is clearing the reference cycles. So basically, the idea is that we are left with this object. And this object, we already know that we have called all the finalizers. There are no weak reference to these objects, and is isolated from the outside. So the reference count that these two objects have are only maintained by the internal reference of both objects. So you think about this, it means that if somehow we destroy these arrows, the object's reference count will fall to 0, and they will be naturally destroyed. So that's the work of an extra function, C function, inside the object, which is called TP-clear. So in Python, you don't need to implement this thing or worry about that. It's implemented for you automatically in the object. But in C, if you are implementing some extension module or some custom class, or even in Python, you may want to implement TP-clear. Usually, we recommend that you always implement TP-clear. So the idea is that even if you are doubting if you need to do it or not, you need to. And the idea is that this function, the only job of this function is remove these internal arrows. So for example, imagine a simple case, the list that contains itself. So for the list that contains itself, this function just deletes all the elements in the list. So it calls list.clear. For a dictionary, it basically empties the dictionary. For a set, it empties the set, and so on. For an object, it basically can set all the attributes to none. And the idea is that after calling this function, there will be no internal reference. So we will be in this situation. And the reference count has fallen to 0, so we know that we can literally destroy the object. And at this stage, the thing that is going to be called right now is the actual destructor. The actual destructor is a function pointer inside the object called TP-dialog that you don't see in Python. But when you're implementing extension modules, you can implement it in case you want to clean up also some other things like C objects or extra things that your extension model needs to care about. And at that point, we have done our work, and these objects are dead, and we just finished. So this is the end of the algorithm and the end of the run. But there is more. So the interesting part now is to talk about some optimizations on top of that, because if you think about this, basically this algorithm runs over all the objects that are tracked by the collector, which is like the majority of them. So there's some optimization that we have on top. One of these is the generations. So the idea is that the generational garbage collector is a optimization on top of this that is based on the idea that objects that remain reachable after a run of the garbage collector, so the green ones in the algorithm that we saw before, will also remain reachable in future runs, because the older the objects are, the more likely to be used by the program. And this idea is basically also in contact with the idea that in Python, there is a lot of scenarios when you create a lot of objects very fast, very little, and very short-lived. So the idea is that objects will be created very, very fast, and will be destroyed very, very fast as well. So if an object has survived a lot of runs of the garbage collector, we probably need to run over it less and less, because it's very likely to survive. So the idea is that we have 3 collections, which we call generations. CPython has 3 by default, but you can compile CPython with more if you want. The first generation, which is indexed by 0, is the younger generation. Then you have the other ones, and the third one is the older. And the idea is that objects that survive a pass in the generation are promoted to the next one. Basically, they are moved. And objects in older generation, as I said, basically have survived more and more collection passes. So if an object in the older generation, the object is very likely to be around for a long time, or at least has survived a lot of passes of the GC. So let's inspect this thing in a graphical way. So the generation in the bottom is the younger generation, then we have another, and the older one. So think that there is some arrows on the top, which I don't know if, so they are there, these arrows here. So these 2 arrows can be, they can be objects that are eternal. So some objects live in the actual data segment of your program, and these objects are never deallocated. So it may be some arrows also from the outside, from objects that will never be deallocated until Python finishes. And those arrows can be also taken into account. So let's do the thing. So we start with the younger generation. We collect, so we run the algorithm that we talk about, and we, after finishing, we know that the objects in gray are the objects that we need to destroy, and the objects that remain blue in the bottom box are the objects that we need to promote. So we do that. So we destroy the objects in cycles, and then we'll promote the rest to the second generation. So some time passes, and there is a new collection in the second generation. So we run the algorithm again, cleaning, weak reference, calling finalizer, et cetera, et cetera. And then after that, we know that all these other objects need to be destroyed because they are not used anymore. Notice that this means in these generation diagrams that there are no arrows from the upper generations to the lower generations, right? So we see that the only object that is blue in the middle is the only object that has an arrow from the upper generation. So after this run, we just promote this little guy there, and then we have the objects in the latest generation. The latest generation is also a bit trickier. It also suffers garbage collection runs. In this case, I'm not going to show it here. But also, when the latest generation is run, there is a lot of extra steps that are done. For example, the free list, the internal free list are clear. So free lists is basically optimization, because when you create certain objects, for example, floats or tuples or objects that are very likely to appear, when you destroy them, instead of destroying them, you mark it as unused. And if you want to create a new one, instead of creating a new one, you use this, the corpse of the other one to put new things in. So this basically makes that it's much faster to allocate them. But when you run in the latest generation, all of the free lists are clear. Some of the free lists are clear. So that you may think, okay, so when you run the algorithm in a generation. So you basically run the algorithm in a generation, what we call a pass of the garbage collector, when the generation reaches a certain threshold. This means that the generation has a certain number of objects inside. And you can actually inspect these numbers. So for example, you can import the GC module, which stands for garbage collector, and then you can call this function called getThreshold, and it will return a tuple. In this case, there are 3 elements in the tuple. It's 700, 10, and 10. Those are the defaults. And these are the number of objects that need to be in the generation to start triggering a collection. In this case, if you have compiled Python with more generation, the tuple will be bigger. You can actually call a function called getSetThreshold and pass n numbers, where n are the numbers of generation, if you want to change this value. This is an interesting trick, as Victor Stinner here will know very well, because if you have bugs that happen in the garbage collector, you want to trigger more collection very fast. So putting low numbers in this threshold triggers more collection, and it will trigger your bug more likely, so you can reproduce it. This is especially useful if the bug are race conditions. So in this case, we set that to 1,000, 50, and 20, and then when we call again getThreshold, we see that the values are changed. So you can use it if you want. If you have an extra knowledge of how often these generations are filled, and you have a better strategy, or you want to delay or make more often garbage collector runs. So you can force also a collection by hand if you want. So there is this function called gccollect, and it receives a parameter which is the generation. So you can make a run on a particular generation if you want. If you don't provide any parameter, it will run on the latest generation, and it will promote everything up. You can actually also inspect all the objects that are tracked by the garbage collector. This is sort of, give me all the objects that are alive in the Python program. Of course, this is not all the objects, because all the objects that are not tracked by the GC will not appear here. But this is still a bunch of them. So the function that you can call is called getGCObjects. So it was like this. You call GC objects here, and then you get this list here, which is very big, so I have not completed. And since Python 3.8, you can actually now specify a generation. So you can say, oh, actually give me all the objects that are in a particular generation. And this is especially interesting if you want to improve the GC or do some experiments of how your program is using the GC or how many objects are in your generations. Okay, so let's talk about the GIL briefly. So the GIL, as you may know, is a mutex. It's actually just a combination of a mutex, a condition variable, and a Boolean. Basically, the idea is that one of the important things that it does is that it protects access to Python objects. So basically, when you have multiple threads, it protects them to modify the reference count, because when you grab a Python object or you refer to it, basically you need to increase and decrease the reference count of the objects, and this is just an integer. So if you have multiple threads accessing the same value, this is a race condition. And because this is a Python runtime, doing this wrongly can create real problems. So as you know, the GIL basically makes that your thread's not happy, but you can use multiprocessing instead. So the idea is that one of the main reasons to have the GIL is that it protects the reference count. That's one of the main purposes. But because we need basically atomicity when we increase them and decrease them. If you go to the actual Python documentation, you can see actually that is explained there. So it explains, for example, the case of a multi-threaded program when 2 threads simultaneously increase the reference count of the same object, and therefore you can have objects that will be leaked. This is never destroyed. or objects that will be destroyed before they should. Other features of the language and extension module have grown to depend on the guarantees of the GIL, but memory management becomes basically the main reason that we have this thing. And this is the reason that removing the GIL is so hard, or one of them, because basically, if you want to remove the GIL, you need to get rid of reference counting. That's it. So you basically need a new garbage collector or some modified garbage collector that will basically do the job that the reference count is doing. And this is really, really hard for many reasons. So the garbage collector is also atomic. It means that there is, first, is only one, so it's global. There is no one per thread. One consequence is that it will stop all your threads from running. We know that because of the GIL, there's not 2 threads running Python in parallel, but it means that if you inspect the times that the threads take, one of them will take a bit longer because it's running the collection. Another interesting thing is copy and write. So what is copy and write? So copy and write is an optimization in some platforms. So basically it's used for fork processes and the like. And the idea is that if you have a process and you fork it, this means that you have a copy of it itself. There is an optimization that says, well, if you're not going to modify the memory, because both processes will have the same memory, so if you're not going to modify it, we can share it. So only when you actually modify some value of the memory, it will trigger a page fault inside the operative system, and then it will make a copy. This means that if you have 4 or 5 or 6 copies of your program, you don't need 4, 5, or 6 times the same memory. But there is a problem. And the problem is that reference counting, because just looking at a Python object increase this number just by looking at it. And because it increases the number, it's writing to memory. And writing to memory copies an entire page. And this is a lot of memory. And what is worse, running the garbage collector increases and looks at the reference count of all the objects that are tracked by the GC. And this means that all the objects, all the pages in the memory layout where this object lives will be copied, which basically will make that if you have 10 processes, you'll need 10 times the same memory. And this is a problem. As you may know, this is the problem that Instagram face, and there's a lot of interesting talks about this. They try to disable the garbage collector. And they have, you may think, oh, is in-memory going to grow indefinitely? So actually, not really. There is still problems, so they actually made some new adjustments in the future. But the idea is that reference count is still the primary mechanism for this. So you will still have a lot of variables getting destroyed because of it. After that, they actually contributed back to CPython and implemented GC freeze. So GC freeze is a function that basically freezes all the objects tracked by the GC. And you can use it in combination with fork. This is basically what is in the documentation, so you can read it there. And you can use it in combination to fork to basically make it a bit easier in this situation and don't suffer that much for this copy and write violation semantics. Once you want to restart the GC over all these objects, you can call GC and freeze. So let's go to some interesting practical applications of this to basically wrap up. So one interesting thing is debugging reference cycles. So you may be interested in saying, okay, I have my program, right, and I basically want to know which objects become part of cycles. Because one of the things of cycles is that it's very difficult to know when they happen, because it's not only your immediate objects, they will have internal structures inside, and they will form cycles of themselves, and they are really, really tricky to find. So one thing you can do is, for example, let's do this situation. So we have our class node there, as before. So we create 2 of them. We point 1 to each other. And then in the GC module, there is this variable here called setDebug. And then you can pass a flag called debug save all. So when you pass that flag, what it's going to do, the GC, is that instead of destroying your objects, it's going to put it into this special variable in the GC module called GC garbage. So in this case, if you follow the code, sorry for the background. If you delete the names and force a collection, you can inspect the GC garbage list there, and we see that our 2 node objects are there. So the idea is that you set this variable, then you run your program a bit, and then you inspect the contents of this GC garbage, and then basically you have an idea of which objects are becoming part of cycles. So you may want to now use maybe weak references, or, I don't know, look at your program to improve it, or something like that. So this is an interesting thing. Another interesting thing is, for example, calculating memory costs. So this is like a simple stuff. And the idea is that the GC, every object for the GC algorithm to work needs to know how to reach all the objects that contains. So for example, a list needs to know how to reach all the objects that are in the list. A dictionary needs to know how to reach the key and the values. A class, all the attributes, etc., and etc. Basically, an object needs to know how to recurse itself. And you can use this thing. So for example, if you have this list here in the top, so it's a list that has multiple lists inside, You may be tempted to calculate the total size of the list, and then you can say, okay, I will call get size of in X, and it reports 96 bytes. And then the problem is that that's not the recursive size of the list. It's only the size of the list plus the size of the pointers. Because if you get this other list here, that one, which has the same number of elements, but they are less because they are not lists by themselves, the size is the same. But you can use this function in the GC module called getReference. So this function here will automatically know how to reach all the objects that are inside. And then you can call this function recursively, and then calling getSizeOf in every element of the list. Actually, there are dictionaries as well. So you can actually know the total size. In this case, I'm not calling it recursively. I'm just calling it in the first level. But you can use it as a generic way of reaching all the objects in a generic one. So the last thing that I want to talk about is an interesting thing that happens, which is exception blocks. So let's imagine the following scenario, right? So we have a for loop there. So we have for x in range something, then whatever. And the thing is that the variable x that we have for x in range, you can actually inspect it after the loop is done. So in this case, range 10, actually the last element is 9. So you can actually print x over there, and you can print the last value of x is 9. This also happens with context managers. So for example, you can say, we'd open something as file, and then you print the variable file, and the value of file is still there. So basically, these variables outlive the context manager, right? So this is a known thing. But if you do exception management here, so you have this try block, so you do try, you divide by 0 to create an exception, and then you do exception as E, and then you print E. So print E works, but you try to inspect the value of E after the except block is done, the value of E is no more. So basically, the variable E is not accessible after the except block is done. And there is an interesting reason for it. The interesting reason is that the variable E contains the exception, but the exception contains the frame object inside, and that contains the variables in the frame, which contains the exception, which contains, so it's a cycle. This means that if we don't do this thing, all the exceptions that happen, and this has to be also thought like when you recurse up and up and up the exception chain, will form cycles. Imagine, for example, that you have a gigantic NumPy array on a function, and then you raise an exception. If the NumPy array is 1 gigabyte, if we don't do this thing, it will leak 1 gigabyte until the garbage collector is run. So it's not a leak technically because the garbage collector will end cleaning it. But the problem is that it will delay the extraction until there is a pass. And if it just happens that your program never creates more objects, there will be no runs. So you basically have to maintain that gigabyte of NumPy object alive forever. It's not important, it's just an interesting thing that happened, and it might change in the future. But this gives you an idea how tricky garbage collection is, how tricky reference cycles happen, and they can appear in the most unexpected places. So the idea that you need to take out is that we have taken care of this. We have put a lot of effort into making it correct, and it's really, really tricky. There is a lot of pieces involved. We also collaborate with other open source projects like Python to try to find bugs related to this and solve them as well. But you have to sometimes, or only sometimes, be aware that there is something called the garbage collector and what it's for and when it runs, and it's related to the guild, and that is very key in case you want to remove it in the future. So this is the end of the talk. I hope you have enjoyed it, and we have now to have some questions.
Okay, we have room for about 3 minutes of questions, so about 3 questions.
Could you provide any example use cases for when you might want to change the number of generations in the generational collector?
So real ones, and with real I mean in real applications, I don't have any that can come to my mind, but one of them is the one that I mentioned before. You have a race condition that only happens in the GC, and this is very likely for C extensions, because sometimes there is memory that is corrupted, and it just happens that the GC, when it's inspecting the object, it crashes. So you want to reproduce it because it's a race condition, lowering the number, instead of forcing new collections. It's a good way of making it appear more often. For real applications, it's more like I try to see what happens and look at the memory consumption, or at least I don't have any that is obvious. Maybe Instagram actually knows something else because they have played with it a bit more. Thanks. Thank you.
Hi, thanks for the talk. Hello. Thanks for the talk. In some of your code examples, you were using del with two variables at the same time. I didn't know that was possible, and I'm a little surprised that del isn't actually trying to dereference or decrease the reference count of the tuple that goes into it. Can you explain how that works?
So it's actually part of the grammar. So it's not really creating a tuple in the middle. It just goes to every variable in that particular list. It's the same thing as, well, it's not exactly the same, but it's the same when you do unpacking and unpacking. So it's not really tuples sometimes getting created. It's just a part of the grammar. You can actually see, so in the documentation, there is a nice explanation of how actually del works with multiple arguments. You don't need a parenthesis, for example. And you can also check the grammar file in the CPython source code. So it's in grammar/grammar, txt, I think. And you can check actually how is the exact way of, or way you can put it there. Yeah, thanks.
Cool, thank you.
Hi, you first-time listener, long-time caller. I was curious, when you have a reference cycle and then you're calling TP finalize, and then something in that cycle resurrects the whole cycle, what prevents TP finalize from being called more than once on one of the things that was deleted first?
So the algorithm first calls TP finalize on everything, and then it checks if the cycle is still isolated, and then if it's not, it resurrects everything. Well, everything that is reachable. So basically, first it runs all the finalizers independently if it's a resurrection or not. And only after that, it actually checks if the cycle is still isolated, and then it runs checks for getting to know which kind of things need to be resurrected and which not. But yeah, that's.
So the finalizers can be called more than once?
No. So it calls all the finalizers, it marks them as called, and then it runs the check for the isolation.
Yeah, but if if the whole cycle gets resurrected and then deleted again later.
But because the mark is there, you know when you try to call the finalizer that you don't need to, because it's marked as already finalized.
All right. Thank you.
Cool.
All right, thank you everyone, and thank you, Pablo.